Hello friends, welcome back to the bench. Our subject today is this tiny handheld oscilloscope from Fnirsi, or Fnirsi, whatever, I call it Fnirsi, okay? Now, I made two videos on the big one, and I love that scope, and this one actually makes me appreciate this one even more, because this one's very limited, but for the price of, what was it, 20 bucks? Something like that. It's awesome. So let's take a look at it. It looks like we require 100 milliamp hours, or the battery is 100 milliamp hours, and it charges with 1 amp. No, not actually. It does have USB-C for charging, so I used the meter. It takes about 2 watts, so it's very standard. You don't need 1 amp charger to charge it up. It is battery powered, battery operated, which makes it actually very useful for some things. On my big one, the big Fnirsi, I connect the big power bank instead of because it's USB powered, which turns this scope into battery powered scope, which is very useful for some cases. And this one is fully battery powered, battery operated, which is great. Let's take this off. There, beautiful new screen. It's pretty small. We have left, right, and press to OK. I don't know what the button actually does. We connect our probes over here. Unfortunately, the probes, as you can see, are not the best. It doesn't. Some of these handheld oscilloscopes come with a BNC port at the top, so we can connect the real oscilloscope probe. This one does not, but there. We have a ground hook over here for whatever reason, or I assume that's to hook up the ground. I don't know why would you, since it's battery powered. But I have no idea why would you need that. But it's there, and that's pretty much it. We have a little strap over here that we can tie it over here. I'll do that later. And it came with a nice USB-C cable and the user manual. Obviously we're not gonna read that. We can figure out how it works, right? So let's press and hold. There you go, and it starts almost immediately, so that's pretty cool. Now a few features. As you can see, you move left and right over here. What we can set is DC or AC coupling, which is pretty cool. I wasn't actually expecting to have AC coupling on this one. Again, why would you need AC coupling if your device is battery operated and comes with just one input and no signal generator? Is beyond me, but it's there. Our time scale goes all the way down to 10 microseconds, which allows you to roughly do 200 kilohertz to reliably see, well, up to 200 kilohertz. Above that, it just kind of doesn't make sense. And we have run and stop, auto, obviously. I don't know what the mode does. Oh, okay, I see what the mode does. Yeah, we can. Nope. Yeah, I don't know what the mode does. It just shows the line over here. But okay, we'll figure it out. First, let's generate some signals and see how it performs. So we're gonna connect the signal generator like so, and we see a nice square wave with duty cycle of 25%, that's what I have set, and 11 kilohertz. 11 kilohertz. What we're reading is 9.9, 9.4, 10.4, because our time scale is a little there. 26, it's showing 26 duty cycle. Well, let's stop it here. 24.4 and 10.9 kilohertz, almost 11, 10.98, almost 11. It should be exactly 11. That is correct. Now actually let's connect the probe of a higher oscilloscope, of a better oscilloscope, and let's see. Yeah, so this one's showing the exact 11 kilohertz, my big scope. VRMS, because I'm using a DC coupling, and here I'm also using DC coupling, so the numbers should match. RMS, VRMS, 1.23 volts. It should be 1.27, very close, negligible difference. 24.4 duty cycle should be 25, which is fine. And 11K should be exactly 11K. It's 10.98, which is pretty good. Peak to peak, 2.56 volts. Should be 2.6 exactly. So again, very close. Very close. For a device of this size, it's pretty impressive actually. Okay, so now let's start by changing the duty cycle to 50%. There. Our duty cycle is almost 51.1 right now, 10.95. It fluctuates, but you know, with leads like this kind of cable, don't expect too much, right? Now let's start ramping up the frequency. So we're gonna go to 10 kilohertz, and now 20. It's showing exactly 20. Look at that. Almost exactly. 30. Showing 30 almost exactly. 40. Now let's reduce our time to 10 microseconds. So that's the minimum. So you can go much higher than this. But let's keep going. 50. Look at that, exactly 50. Well, at least it was for a second. And exactly 50% duty cycle. It can be pretty accurate actually. 60, 100 kilohertz. And now we see that at 100 kilohertz we can no longer observe the actual waveform. So on the big one, you can see I can see the signal exactly. I can zoom in very nicely. On this one, It won't zoom in anymore because 10 microseconds is our maximum resolution. So I would say reliably it can go to 100 kilohertz. It comes as a 200 kilohertz scope, and that's what they say over here. Let's see if I can find some English here. There. 200K and 2.5 megasamples per second. Oops. There. 200K and 2.5 megasamples per second. That's not a lot. 2.5 megasamples per second, that is not a lot. Division 10 microseconds. Voltage peak to peak 80 volts, and of course we can do X10, which is here. So we can it's basically the voltage divider. Coupling AC/DC, very nice, and that's pretty much it. So since this is 200 kilohertz scope, the rule of thumb is that you use it up to half of its capabilities, right? That's going to be a reliable range. This one that I have over here, it does 1 gigasample per second, and it goes to 100 megahertz. I tested it on the highest frequency I tested it with is the ECM crystals, which is 10 megahertz. That was the highest frequency I measured on this one, but it still had plenty of room. So let's up it to 200 kilohertz. This is our maximum designed, or maximum described by the data sheet. There. So let's break it. 300. We're still reading 305, 308, so it's going off slightly. The duty cycle still works, still shows pretty good duty cycle. So now we're off by 8, maybe, now 11 kilohertz. That is more significant, but now we're operating outside the designed region. 400K. 400 kilohertz, it still gives us a pretty good estimate, right? If you had a 400 kilohertz signal and you just want to confirm that the signal is there, well, this is roughly what you would see. So you can't really even determine whether it's a square wave or a sine wave or anything like that, but you have rough estimate of frequency, which is not too accurate, but it gives you something. It's better than nothing, right? Let's go to 500K. We have 517. Now our duty cycle dropped to 40%. It's still at 50, what we were generating, but obviously now the scope can't really figure out the duty cycle based on its capabilities. It's just not capable of measuring those samples. It's just too fast. 500K. But we're operating 300 kilohertz outside of our nominal region. 600K. Now it says 50% duty cycle, which is correct. Our VRMS is completely off, but that's expected. It's still relatively, again, if you just need to confirm that the 600 kilohertz signal is somewhere, you can confirm that it's there, right? You can't reliably measure it or see it exactly or analyze the shape of the pulses, but you can confirm that it's there. 700. Oh, and now we're breaking. Yeah, it dropped to 500, 600. Yeah, So definitely 700 is way outside of the capabilities. 800, 900, this is 1 megahertz. Yeah. So this is nonsense now, but that's to be expected, right? Okay, let's go back to 100 kilohertz, and actually let's drop it even more. Let's do 40 kilohertz, just so we can see the signal. Actually even 30, because now let's check other types. So this is our square at 50% duty cycle, and now let's do triangle. I'm not too happy with this. So these should be straight lines. This should be straight lines. They are not. Let's drop the frequency. Now let's operate on 30, because it has a problem with stabilizing. Now it's better. So our frequency should be exactly 30. It's close enough. Duty cycle, well, there's not really a duty cycle on a triangle wave. 745 millivolts, 0.70. It should show 745 millivolts RMS. It's pretty close. And peak to peak should be 2.57. It's 2.4. It's really close. Frequency, really close. My only complaint here is that in triangle you can see, actually let's even go further here and let's pause it. You see the ripple? That is because we only have 2.5 mega samples per second. So our resolution is just pretty low. Well, that's to be expected. Again, this is $20 device. Don't expect too much from it. Okay, so let's continue with sawtooth. And the same thing happens here. So you would expect this to be a straight line, because it should be. And we have some rippling over here and over here. Also the shape, it's misshapen slightly. So this line should be completely straight, and a sharp angle over here. We have smoothing over here. That might not only result from the poor performance of the oscilloscope, but also from our cable, our probes. So this might not even be related to the scope, this thing here. Well, let's do the other one, and this one pretty much the same deal, right? Now we have a sharp over here, but again this should be a straight line going up, and again a sharp angle over here, right? You can see it on this scope, right? It's perfectly straight line and sharp angles because it's low frequency, right? So we can see that if this was megahertz, this scope would also give you some issues, but at low frequencies, that is our expectation. Here we have distortion, and I would guess that this is a result of the probes, not the scope. That would be my guess. Let's see the step. So here we have the even more distortion. So the signal should look like this, right? Nice little staircase going up and straight down. Staircase going up and straight down. And here we can barely see the staircase. You wouldn't even recognize it based on this image. And again, the shapes are not shaping. But here it's actually, this looks like not a problem of the probes in this case. This looks like purely we don't have enough sampling, which is odd because, you know, we're operating on 30 kilohertz, which actually now shows 2.25 kilohertz. One point seven, 3 point, yeah. It can't really measure this for some reason, which is odd. Why wouldn't it measure? But it is relatively complex signal, so we'll forget that. And that's our half sine. All right, so this is what you would see when you just get the sine wave and just diode out, just a single diode, half bridge, or just single diode. So we have half of the sine wave. It measures nicely, 30 kilohertz. Duty cycle, well, again, this is not exactly duty cycleable, but it looks like it's roughly 30%, right? Yeah. VRMS, very close, should be 112. And peak to peak, 251, should be 257. Very close. I'm happy with it. And let's stop it. Yeah, we have some rippling over here. We have some deformation here and there, but what did you expect? And now we have beautiful full wave. So this is full bridge rectifier. So our bottom side of the sine went up, right? And well, now it says 17K, 20K. It really, this this signal really messed it up, just like the other one. And this is way off. See, if you wanted to rely on measurements of frequency, this would tell you that, oh, something's wrong, because you can see the wave perfectly, right? And you're reading 20 kilohertz and you expect it should be 30 kilohertz. So yeah, you start replacing crystals and and debugging what's wrong, because the wave looks good, but the frequency is off. Well, that's what you get for 20 bucks. Exponent. Again, 21K should be 30, but this is relatively complex. It actually shows really well. Yeah, this one shows pretty well here. I'm happy with this. There's some distortion here and there, right? It's not perfect, but this looks good. Now, this looks pretty decent. Again, the sharp curve over here, it should be sharp, but overall, it'll show you some signals for sure. Exponent, square root. Yeah, it's messing up. The square root is messing up with the sync. You cannot sync to stabilize the image. Now, this one, oh, this one looks good. And look at that. frequency is very close, and it looks pretty good to me. This is actually not bad. I was expecting worse, because take a look here on my other scope. It's having problems synchronizing, right? Stabilizing the image. So that's even better than I thought. This one, oh, perfect, 30 kilohertz. Very nice. This actually looks really nice. Exactly what I see on the big scope. And perfect frequency. Perfect 30 kilohertz. This is very nice. This is very sweet. Now these, yeah, I wouldn't think that custom would actually register. Oh, why? The frequency is way off for sine wave. Why is the frequency this much off? By 4 kilohertz. Not even 6 kilohertz. That is weird. I would not expect the frequency to be this much off on a perfect sine wave. Would you expect that? I didn't. Well, so reliably we can work on the frequencies. It's actually hard to even say which frequencies you can reliably work on, because we're off on the 30 kilohertz signal, which is sine wave. So this is 10 kilohertz now. Let's up our division there. Okay, that measures nicely. 10 kilohertz. It looks pretty. This is 1 kilohertz. And it measures perfectly. Now, this is 100 hertz. This is also pretty well. This, yeah, pretty accurate. Very nice. Now let's continue going down. 50 hertz. Yeah. So this is what we would see roughly if we connect it to the outlet. All right. 50, or was it 60 hertz? I think it's 60 hertz in the US and 50 hertz in Europe. But roughly this is what we would see. So let's go to 10 hertz. Very nice. Two seconds. Let's go to 1 hertz. And This looks pretty good to me. This is the lowest frequency I can achieve. I can go below 1 hertz. Our frequency has not measured. It's a 0, which is pretty close to 1. A 0 is pretty close to 1. So we're off by 1 hertz. Right? If this showed 100 hertz, I know that we would be way off. But 0 is pretty close to, or yeah, 0 is pretty close to 1. But you can see how you could use this to just kind of monitor the voltage on something, right? Not even drops, because it's obviously it's not going to show you quick drop, because it's sampling roughly maybe once a second, maybe twice a second. It's roughly the refresh rate here. So it's not gonna catch the drops or peaks or anything like that. But if for whatever reason you just want to perhaps connect it to the car battery and just kind of observe over time what the voltage would be. Right? Actually, let's even let's try that. So let's connect to our power supply. And now we dropped to 12 volts, went up to 12 volts, and now four volts there. So this is 3 volts now. It doesn't seem very stable. It's not showing up as stable, even though our voltage is stable. This is coming from the stabilized power supply. Let's start dropping slightly. This is 2 volts. Oh, and 2 volts is showing up nicely. Yeah, so our 2 volts is what we expect. There's a little bit of something there, but overall it looks okay. But when we go to 2.5, yeah, at 2.5 it's already experiencing issues. Oh, now it's stabilized. Okay. 3 volts. Yeah. So on 3 volts, it just, yeah. What did they say? Didn't they say it was voltage range 40 volts. What? 40 volts? This is 3 now. Because we can't. Oh, right. Yeah, we can control this. So 2 volts per division. Right? Okay, and now it's rather stable. If we have 1 volt per division, we get the wrong reading. So its operating range is somewhere here. Up to here maybe. Let's see, there was a little shape over here, a little bump, but this looks good. So now let's go to 4 volts, and it's also looking good. Okay, 5 volts. Okay, 6 volts. Let's speed it up a little. Hmm. 7 volts. And it's still showing up nicely. So why would it, at 3 volts and 1 volt per division, it's experiencing issues? And at 2 volts per division and 8 volts on the input, it's showing up nicely. Now 5 volts per division, and let's keep going. 9 volts. Oh, this does not look good. Not one bit. 9 volts with 5 volts per division. This is huge distortion here. Huge. It should be like this here. All right. Let's go to 10 volts. We can go up to 40 on this one, right? Yeah, still distortion at 10 volts, at 11. And 11 looks better. Oh no, not anymore. Yeah, it looked good for a second here. For a second here it looked good, but now it's distorting again. It's very annoying that these parameters are overlaid, or these measurements are overlaid on the image. It's kind of annoying, but I can live with that. 12 volts. And 12 volts looks not too bad. So far so good. Look at that. So what is going on here? On the sound, so if you wanted to use this to observe the power, the ripples and stuff, right? On some voltages you'll see nice smooth line, and on some voltages, seemingly for no reason, you get distortion, and on some voltages even significant distortion. This is 13 volts, and here we have huge distortion, right? What is the difference? We can't really blame the probes because we're working on DC, right? This is pure DC signal. So I have no idea. Is it the reference issue? The reference voltage issue? Maybe. 14. And 14, well, looks better than 13. Slightly. Um, 30 volts. let's up the division to 10 volts. 10 volts per division. This is our 30.1 actually. And again, big distortion. On nice DC voltage. Peak to peak shows 35, which is 30.1 in reality. RMS shows 27.5, which again is 30.1 in reality. But with distortion this big, yeah, now it's showing 33 volts peak to peak. Unless it's just using that again as that might be messing with the measurement. Let's see. Oh, 1.2 volt peak to peak. So these peaks over here, this distortion, according to the scope, is 1.2 volt. Because this looks pretty good. It's 30.1. It shows 30.2, 30.5, 29. But the distortion that the scope itself is showing is 1.2 volts. Which is huge on the, I don't know, stabilized power supply. It's huge. We can't go over 10 volts, so this is our maximum. Let's go to our maximum voltage then. Oh, I can, okay. My power supply won't supply more than 31 volts. So this is our maximum. And meh. Meh. Well, do consider that this is extremely cheap device, and if you want to make more reliable measurements, you need something slightly better than this. However, my big Fnirsi, that is, I don't know, 3 times or 4 times the cost of this little one, has been reviewed by many other technicians, and some concluded that it's completely awful and I wouldn't touch it with the 10-foot pole. Be that as it may, because obviously it's a very affordable device, so it will come with some limitations. Compared to this little one, it's this scope is awesome. This one, well, how much was it with shipping and everything? $28.61. $28.61 for an oscilloscope. I say that's a pretty good deal. However, not for measurements, just for, I don't know, confirming the presence of the signal. Maybe measuring roughly frequency, but frequency measurement is so unreliable that I probably wouldn't try to use it for that purpose. The frequency range of 200 kilohertz, that's, or actually even 100 kilohertz, but reliable, the maximum, absolute maximum of 200 kilohertz, that really limits your ability to use it for, well, what would you use it for? For anything other than the audio devices, right? You can make some measurements, some calculations using the RMS over here and peak to peak. When you want to perhaps measure the output, the full RMS real power output of the amplifier, and you give it a 100 hertz sine wave, right? That would be useful. But the main selling point of this device, in my view, is its portability, right? Because that's what you want this device to be. You put it in your pocket. Oh, this is not gonna work for much longer. Too bad this is not a screw-in, because that would be a little better. Because I feel like if I put this in and take it out a few hundred times, it's just gonna give out on me. Then it's gonna start wobbling a little bit, which will affect my measurements. Yeah. Portability. That is what the selling point of this device is. It's really small, it's really light, but it feels, it doesn't feel cheap. It feels nice. Hey, focus. It doesn't feel that cheap. It's properly heavy, right? I don't know if there are weights in there, but it's a lot heavier than I expected. I don't know how much it actually weighs, but it's a lot heavier than I expected. That's probably mainly because of the battery. We have 2 screws on the back. I will probably disassemble it and see what's inside, because I'm curious. Yeah, it's a handy, nice device. Would I recommend this? No. There are other options you can get, maybe slightly more expensive, but not as compact, not as neatly done as this. So this is definitely, portability is its great benefit, or great aspect of it, portability. But if you have such unreliable measurements, again, what would you need it for? What would you need this device for? I'm not sure. I will figure out the use for it, because I already bought it. So I have to do something with it. Or perhaps I'll just gift it to someone. We'll see. But yeah, you have plenty of other options on eBay for cheap oscilloscopes. Some you can even build yourself, buy a kit, DIY kit, and build the scope. Others just are not as neat, not as portable, but at least you can connect the actual oscilloscope probe to it. To this one, you're kind of stuck with this. Not too impressive, guys. I think this version, this is early version, and I do believe that it requires some more work on this. This is not finished product yet. And I'm not only talking about reliability of measurements, although that would be nice if this could measure more accurately, but the ability to use the probes, maybe the screw in, or, well, the reason we don't have BNC on it is because it's this big. It actually would fit. Yeah, it would fit just right. Just right. It's like almost exactly the size. So it is possible to give it the actual port BNC to connect real probes. So it would be doable, and I would like to see that on this device, because then we could at least eliminate the possibility that it's the probes that give us problems, not the device itself. Right now we can't confirm that. So for now, it looks like this is a very nice device with a very limited use case. And once I figure out the use case, I'll definitely let you know. Alrighty, fellas, we're gonna stop here. This is Fnirsi. Oh my god, yeah, there's a model here. The model is DSO 152. So we're gonna wait for DSO 200 before we recommend this one. At the moment, not recommended. Sorry, I know it's affordable, but you probably won't find much use of it, most likely. Alright guys, I hope you found that useful. Thank you very much for watching, and I shall see you in the next one.
If your Subaru Outback doesn't run, number of working injectors is one.